Hi everyone. Today we'll start like in 5 minutes, as usual. And it's kind of one of the last lectures of our course. Okay, I think it's time to start, and I'm happy to see everyone who has joined. Unfortunately, there is not big attendance today, but I hope other people will also join. Because today the topic is quite interesting. I think that we got told a bit about transformers and how can we do better with transformers today or last time. We gave a seminar, or maybe not the last time, but whatever. Today, I will cover the main ideas that are connected to improvement of the processing of large sequences by transformers, and how can we manage to solve challenges that rises. As we all know, transformers are pretty good in many areas, and the main idea is the following: that we kind of calculate attention between pairs of queries and keys. So if you have like a query, which is a feature vector, and also you have a, a key, which is also a feature vector, you can say how query is related to a key in the database and calculate the attention score as a scalar product of these two guys, for example. And so if you have attention, you can instruct the information and so be it, and you can run your this guy to solve your favorite model. And in a similar way, we can write down this kind of representation of idea of transformers attention in as a formula. In this case, we can say that our attention scores is softmax of the product of two matrices, queries matrices and keys matrix, and we modify the embedding we have as input to our layer of attention. There can be multiple layers like this. For example, in the original attention isolation paper, we have like 6 layers of this type that are inside of a bigger blocks of layers with feed forward and normalization and so on. But what we're interested in right now is that we have this attention scores and that we obtain them using this standard. When we are processing the input of our sequence-to-sequence architecture, we are doing self-attention. In this case, keys and queries are similar guys, and we just calculate pairwise dot product between the different parts of our model. And so the formulas are like this. We have separate weight for Q, separate weight for K, and maybe some weight from W from V, and we get them all from embeddings of our initial vectors. And the size of this embedding can be like Gx, and Gq, for example, is the dimension of this weight matrix to produce not like initial embeddings, but queries or keys. And what that we call self-attention, and the complexity of the processing of this kind of data is equals to the length of a sequence. So if you have like G, or not D, sorry, it's n squared here and squared here. When we have n tokens in our sequence, we calculate the output of our attention layer using like O and squared operations. And what's even more important is that the memory requirement is also n squared. And so it means that for large sequences, it's not possible to proceed them right in this transformer way when we use vanilla transformers. And what's more important is these tokens in modern models are not even words, but they can be a character level model, or it can be like part of the word. And in this case, we say that number of tokens is greater than number of words in our sequence if we are thinking about uh, like modern models and processing of text with these modern models. And so we have this full matrix that we calculate in O and squared. So we have this input and we have the output of the same size after weighting using attention weights what we have as input. So it's basically self-attention block and computational complexity. And as we can see, it's prohibitive. And like models like BERT use something like 512 tokens. It's definitely not enough to process large text. For example, we can consider like a very generic problem to summarize text from this very popular CNN Daily Mail dataset. And in each text, we have more than 700 tokens. And so we can do it with our specific tricks for our pre-trained BERT model. Also, it is the case not only for texts, but also for DNAs. In this case, we can also try to use sequential data processing models. We can say that we have a sentence in this 4-level alphabet A, T, G, C, and we can try to process this kind of data with transformers, and a number of tokens is something like 4Ks, even if we use not the coding of each symbol as a token, but if we group them, like I suppose that in this case it was like 6 or 5 in this block. So again, we encode this guy as like a token, but we have more tokens than we can eat when we are talking about fast working models relate based on transformer architecture. And for bound transaction, we obviously have something more. Okay, I just count how many transactions I have this year, and it's more than 1,000 transactions. So I think that for other people, it's something like this. And so we again don't have enough capacity in our model to proceed this kind of data. Okay, we can try to do it like with vanilla BERT or more general transformers, but in this case we can stack because the train will be long, because it's not kind of very fast. I think when we're working with it, and what's even more important, we have like kind of memory limitation and it's very hard to do it. Okay, let's start with a very generic idea of what we can do with this problem, with the problem of processing of long sequences with transformer type architecture. First thing that I think comes to mind when we're thinking this kind of problem, we like doing split 2 blocks of our long sequence. And so for each block, the length is smaller than 512. And so we proceed then with BERT. And so we have kind of embeddings after application of our model to each sentence. And then we somehow combine all these guys to have the final embedding. And in this case, okay, it's pretty easy. I suppose to construct some kind of model that aggregates separate sentences. For example, we can use max pooling when we take the max value of each embedding, or we can think about something like bin pooling, or maybe we can run a separate transformer model or train an RNN model and so on. But it's kind of not natural way to do things. We have to carefully select what we're doing in this scenario, and in the end we can have something that's not as good as we expected, especially if you want something like end-to-end training and adaptation to downstream tasks. We should backpropagate through all those guys, and it again becomes a computationally cumbersome problem, quite hard to solve. Also, it can be hard to capture cross-sentence context. If we say that we have some word like friends here, and the friends becomes she or he in this sentence, and again we are thinking about like this a language which would be definitely related to friends if we go back in time, but if we don't have access to this information, then we kind of can't capture this context. And so we are again in a situation similar to what we have when we were talking about RNNs, and we kind of misinformation and can't create the model that is good at generalization at the level we want and capturing information how is like distant context if we are thinking about sequences in this scenario. So it's kind of not very good solution, and maybe we can think about something different, something better, something what we can do to improve this particular model. And there was actually kind of a number of packages, a number of talks that were devoted to improvement of transformers, and it's kind of extract from long format paper, and it's kind of 2020, so I suppose it mentions most of the works that are related to improvement of attention for processing of long sequences. Yes, you can see some of them may be familiar to you, like transformer XL and so on. And we can try to make like a general conclusion of what solutions can work and what solutions cannot work if we are thinking about trying to process long sequences. And we can see that there are generally two big approaches to this problem: LTR and sparse. LTR means that we proceed from left to right. We start from some sequence, and okay, we kind of split the data to bunches, kind of what we were talking during discussion at the previous lines. And we proceed like have some kind of embedding, then proceed with another embedding, and so on, so on, so on. And so in the end, we have like answer to a classification problem, for example. And this is one way to make transformers faster. We are doing like n is 0 squared, when 0 is the size of a chunk. Also, we can try to improve in a different way. We can say that now, like our vanilla transformer model, we have a relation all to all. The transformer model says that each token in the input is somehow connected to another token in the input. We can try to lift up this requirement and try to make it more sparse and say that each token in the input sequence is connected only to part of the tokens in the input sequences. And this what we can call sparse attention mechanism. And later we will consider in details more approaches that tries to elaborate the sparse way to think about improving transformer performance. And okay, let's draw a figure to conclude the slide. So kind of when we are thinking about sparse transformers and we see how tokens connected at like L-1 and L's layer, we can say that in transformers, in generic transformers, we have this one-to-one connection, and each node at previous layer is connected to each node at the next layer. And it's the thing that makes our computational complexity n squared. We can try to somehow say that we are not interested in all connections, and maybe we should focus only on some connections. And for example, we can limit our number of connections between the node of output and the node of input to like k. And in this case, we see that instead of n squared, we have n times k, because for each of these n tokens, we only have to do k operations, and it results in the improvement of the complexity, especially if k is significantly smaller than n. So this is a way when we want to create sparse attention pattern, and later we'll consider how can we implement this and how guys out there in science and industry are doing it right now, because most of the work we'll be talking about is about 2020. So it's kind of very recent research in this area. And okay, I hope you can understand why it's so important to make transformers work faster, especially if you're thinking about like this general idea that right now we have like billions of parameters in transformers, and it takes a long time to infer, and so it costs money for companies to run like the transformer each time, and also it's very expensive to train transformers. And this is what we are seeing when we think transformers and like something like GPT-3 or whatever, and they proceed not very long sequences. And even in this case, we have to burn like millions of dollars to get output of the model and to train the model. And so it's very important if we can cut these expenses and make our transformers smaller, more focused on the right things, on the right connections uh, between the nodes in our connection graph between tokens. And so what that will do there. And also I would like uh, to emphasize these two things too. So kind of we have two additional degrees of freedom at what level our language model works. Here we see that we mostly focus on character level language models. So in this case, each token is a character. Okay, definitely can be other possible options. And also about pre-training, it would be very good thing if you can start not from the scratch, because it's very expensive, a long procedure to train your own transformer. But instead, you can try to download a model from your favorite library and somehow fine tune it to get better results in the end. And as you can see, some approaches can do it, and it would be important to uh, okay, understand why they can do it, why we can use pre-training, and we can use create already created large models to improve the processing of large sequences. Okay, so I think it's the end of this introduction part. And as usual, I want to ask a question to you. If everything is clear up to the moment, and if it is, please write a plus sign in the chat. So I will understand that it's okay to move forward and that we have a solid background on what is transformers, what is attention, and why self-attention is somehow ruining this nice word, because we need very many resources to to obtain the result of the model and to train it too. Okay, so let's go on. Okay, we will start with a paper called Long Formers. And so let's describe why it's important, why they like kind of work better. The reason is that as you can see from this paper, yes, many works are related to this kind of data. Also, I think it's kind of important to understand that it's not can be not only applications related to the processing of texts, but also applications related to processing of other types of data. And in this case, you are mostly limited to the character level. Okay, as you can see from this slide, here we have this full self-attention, like the starting approach, like BERT, vanilla BERT. And we have another guy here, like this long former, or another options for long former. Three of them here in this plot. And as you can see from the right figure, the memory required to process full self-attention grows like x squared in this plot. And you can see that for 3 other approaches, the requirement for memory is kind of significantly smaller. And you can imagine then, okay, your server, or even your PC, it will be like 16 gigabytes of memory is kind of here. And in this case, we can say that if the sequence length is greater than 10,000, then it's not possible to proceed it. So it's kind of our only option to do this kind of things. So let's find out how can we achieve this super performance compared to what we have for our other transformers. The idea is to combine different types of attention. As we already discussed, if you have this full attention, then we have n squared operations to proceed one layer of attention. Instead, we can adopt different ideas actually from CNNs that we discussed last week. The first idea is sliding window. We can say that we don't want the full attention. We don't want to produce this J's output. We want only to create attention vectors from only part of the sequence. So in this case, we apply this same formula, but we use kind of specific Q and K matrix because we kind of weight only part of these guys to get the output. And if the window size is hash, so this length of this window is hash, then we only need hash times n memory and computations to proceed one the sliding window attention layer. We can say that maybe we want more background for each token. And in this case, we try to do dilated sliding window. Again, we can say that there are hash elements here. And they are just a bit distant from each other, and we miss some of them because we think they are not important. Or maybe we can say that if we have many layers, and in any way we have kind of combination of these guys in the end, so it's okay to have dilatation. So in this case, for window of size hash, it's kind of hash elements we use in our dilated sliding window approach. We have the same computational complexity and memory complexity. And the last one, but very important one actually, is global attention. In this case, we say that we need specific tokens that are related to all other tokens. For example, we can say that this can be a token that is used to solve some kind of downstream task in the end. For example, to say if this review is negative or positive, or what different classification task you want to solve. In this case, we again see that we need only G times n computations and memory, where G is the number of these global tokens that we use to calculate the attention that affects all the tokens and also that is related to all tokens too if we want to calculate the final attention for each output. We kind of, when we combine all these types of attention, we pay attention to global tokens, pay attention to sliding window. And this is basically this long formal architecture. And for sliding window, okay, I can repeat that we need to do something similar to convolutional neural networks. And the reason is that like we want to start from neighboring tokens. And also in the end, as we have many attention layers, we can say that our receptive field grows. For example, if we go back to this convolutional neural networks and see if we have a filter of size 5 by 5 for image, and we want to find out what is the pixels in the initial image that affects this particular pixel in the output of the second convolutional layer. When we go one layer back, we can say that this receptive field is 5 by 5, and it equals to the size of the kernel. When we go one step back, we see that right now we have like 9 by 9 receptive field, and we see that if we have enough layers, our receptive field equals to the whole image. So if as our neural networks are deep, then we kind of don't need this full attention. It's enough to have the sliding window, and after application of number of rounds of attentions, we say that, okay, we have tokens and depends on like 5 tokens, for example, and then we go back one layer more, and we add 2 additional layer, 2 additional nodes here, and so on. And so if you have like deep transformers, and we usually have like 6, maybe even deeper one, then we are able to capture the dependencies and to make this work. And right now we are kind of can do similar tasks with matching very distant parts. Also, we have another way to manage global dependencies. This is specific tokens that are called global tokens. We have G of them, and an example here can be like downstream tokens that we add to the beginning of the sentence, or a kind of separator token in the middle, kind of the information we need for the end of each particular sentence. And if we add these guys, and as you can see here, we have a combination of global and sliding window, then in the end, we kind of have everything we need. To make it work, we also need some tricks. And so let's take a look at what kind of tricks are useful when we are talking about long formats. Training is not something that we are doing at a constant rate and at constant sizes of attention windows. Instead, we start with short sequences and small attention windows. And in this case, we kind of can teach something, then we expand these windows and take longer sequences as input. And so in the end, we kind of have, after 5 stages, number of these phases of training is 5. For long form in particular, we have the processing of those sequences, and due to this trick, we don't stuck in very bad local optimum, and instead we kind of have good one, and we are able to train these long range dependencies. So it's kind of good. But it's important to see some parts of this hyperparameters to understand what's really has been done by this work. And the last phase is 5. So this is the model we will use later. And we see that the window size is 512. It means that instead of something that you can imagine that you have like this small field, small window, like of size 5 or 7 when we're thinking about CNNs, instead we have, okay, kernel of size 512. And it's kind of similar to what we have with this usual burst models. And this is kind of make this magic not that efficient and not that amazing that, okay, the actors, the papers are trying to convince us it is. But due to this fact that we have very large windows, we can try, for example, take some parameters, not from scratch, from the screen, from very scratch, but use this fine tuning. We use this BERT model, and for BERT model, we have this exactly number of tokens. So it means that we can initialize our window parameters with these guys that we have already trained for many epochs, and not we, but some other guys on the internet with 100 GPUs. So we can make it more effective and don't spend time on like this initial tuning of the neural network. Instead, we start with kind of reasonable model, fine tune it, and in the end have something good that we can use for our own good. And also about global attention. It's also not something that you have like 2 or 3 tokens all the time for global attention. As you can see from this figure, again from the paper, 2, 3, 4 for global attention. Do we have global attention tokens all the time? Not. Sometimes authors suggest that we have only one of them, or like kind of a number of them in the beginning of the sentence to solve downstream task on the base of the output of this part of the sequence. For some other data sets, they say they even don't need the global attention. We are doing well with window attention, and it's completely fine. But sometimes when we are thinking about question tokens and answer candidates, and we say that we need tokens that's specific to each question and to each answer candidate. So it can be quite a large number of tokens. But I think not very big, so I think 10 to 20 max in this article at least. So it's doable. It's not like 512, tremendous number. And so this is the end of the story for our first model. So let's go on and see what else we can do, or other people are doing right now about this kind of models. And the next candidate is Big Bear. It's even more recent paper, and they try to go further this route of combining different attentions. You already know what is window attention, what is global attention, but Big Birds adds another attention called random attention. Now the paper does not specify if this attention is similar between different attention layers or not, but I suppose it's different. And for each new attention layer, we generate it from the scratch. And we say that we uniformly at random select pairs of tokens, and we say this output, for example, depends on these 3 random tokens, and another one depends on this 1 random token, and so on. So we add this additional attention layer to make the connections between different inputs and outputs stronger. This is what we lack when we are thinking about window attention, because we need many layers to make like a good connection between very distant layers, because to connect these 2 guys, we need to go there and there. It can be very hard to train, for example, parameters that try to capture these long-range dependencies. And for, okay, if you say that number of random connections between input and output is R, then the time and space complexity for this random attention is R by n. And as what's similar to the last approach, we say that R significantly smaller than n, H2, G2, and so in the end we have complexity O n for each attention layer. And okay, we combine all of them to have this big BERT model and have like good processing of very long sequences. Also, we can try to prove something about these models and what theorems from these articles say. At first, they can say that if you have like a continuous function f, and we have this function g generated by transformers. So it's kind of our model. We can say that they are not very far away from each other. We can say that f minus g is no larger than some kind of epsilon. If you select like the large enough number of layers. There is one thing that we need to understand about this is that we need to have in this attention node that is connected to all other nodes. And this is why we need, at least in theory, this global attention, because global node is connected to all other nodes in our graph of sequences. And we kind of have this star graph S here. And we can say that for universal approximation, we don't need this random attention, we don't need this convolutional attention. Instead, we are happy with this global attention if you're looking from theoretical side. Also, this big bird is Turing complete, and we can calculate everything in the end, which I think is good, but I suppose there is no surprise in it. Also, it's important to state that there is some limitations when we're considering these models. The proposition in the article says that sometimes to solve some kind of problems, in particular, when we want to find the vector that is farthest from the R vector for each token in the sequence, then we, in worst case, will need O n layers. It means that to calculate each layer, we need kind of k times n, the k equal to r plus g plus h. And so the total computation costs is the product of number of layers and computational costs for each layer. So it equals to chi n squared. And it means that in the end, in worst case, we have similar problem to what we have in transformers. So we need many layers and we need like much memory, much computations. But okay, as usual, we can expect that this is kind of very careful estimate, and in reality, it works better. And we can say that this big bird for some problem works better when we see this like 3 databases with a large number of documents, and each document has large number of words. We calculate some score, and this big bird works better. And we can say that it works better if we are thinking about large models, about base models like transformer plus Roberta, and update of this Roberta by big bird with these types of attention. And also they're kind of comparable to the state of the art. So if you think about processing of large sequences, you can have like 2 ways. This first way is being trying to apply an heuristic, and another way is to try to apply big bird or long former. Also note that there is kind of tricky things that allow better computations. At first, we say that we can improve utilization of GPUs and TPUs when we are doing one attention layer. If we have blocks of computations, we have not separate cells here for random attention. Instead, we generate them by blocks. And it is more efficient because we kind of group them, rearrange them, and have in the end more solid way to compute the output. And another note is that we can try to reorganize computations and to have this like dense computations instead of sparse computations when we think about big bird. So we like kind of recombine all those guys to get this full matrix and get the result. You should know that this is not the exact result, and we have some edge effects here. when we're trying to like combine them in the edge, like that. But who cares if it still looks fine? And I think that we can even prove that it's not much difference actually here. We also should devote some time to discussion of hyperparameters for Big Bird. And they say that in general, they recommend to have block lengths 64 blocks. This was introduced here and here. This is the size of this guy. And we calculate all other hyperparameters on the base of all the size of the block. For example, number of global tokens is 2 times b. For window length, 3 times b. Number of random tokens, 3 times b. Okay, is it good or not? Not very good, actually. You can see that in actual settings, we kind of have not much smaller model than you can imagine with this kind of model. Again, we say that number of global tokens is kind of similar, at least when you're looking at the order of magnitude to what we have as a whole sequence length with traditional models. Let's have like, again, I repeat, 512. So not very large difference here when you're looking here. And for window lengths too. So we kind of try to put almost everything here when we are thinking about this kind of transformers. But at least we can try to say that it's at least good. And so this was like kind of the first idea of combining different types of attention, and 2 types of attention blocks we combine here. And I think it's time to ask you a question. If everything is clear and do you want to go further, please write plus sign here in the chat. In this case, if not, please think a bit and ask some questions about what's going on right now. Why we are still talking about the transformers? Okay, do you have some specific questions? I can try to answer them. Okay, it seems that like the idea is pretty straightforward, but maybe it's something that I miss. Okay, I hope it will be good this way. Thank you for the feedback. And let's go on to the next stage of our course. In particular, I want to talk to you about another model. I suppose that Rodrigo maybe told you a bit about this stuff, but I hope I will not confuse everyone if I repeat it one more time. The idea is that we want to somehow reduce the time and memory complexity for transformers. Again, we have one problem today, at least me. And we want to pay attention to specific tokens. And what is the motivation also? Is that when we are calculating softmax, actually these tokens that are have very small scalar products with a particular token, they make very little contribution to the output, and because the weights become very small after softmax. So actually, when we are computing attention, we mostly pay attention to very small number of tokens with high attention scores, especially after softmax. So maybe we can somehow try to select these tokens based on some heuristics. And in this case, it would be like good in terms of memory complexity things. And we can reduce this L squared, where L now plays the role of length of a sequence to something more doable. So instead, we kind of say that we have a kind of number of neighbors here. And so instead of L, we use different guys with this reformer. We say that we have this MR, and this MR is number of buckets with number of other tokens related to the particular token. And also, when we're thinking about trying to group objects into some groups, we have like a term bucket, but you can also see this as clustering of tokens. If we will manage to cluster the tokens to like clusters, each cluster contains only similar tokens, then we can say that we kind of succeeded our task, because if you have similar tokens in each cluster, then only them with high probability will contribute to the attention score. And so we can say that we lose almost nothing in terms of accuracy, in terms of how much attention we get to the next layer. But we will improve the overall time and space complexity of the model. And to do this, we do hashing function. We say that we have like a map from X from embedding to hash. Hash is an index of a bucket. We are talking, Margarita, we are talking about similar tokens. We say that each bucket will contain similar tokens, mostly. Yes, this is our goal, because we are thinking now about at token level. We won't just like say that, okay, we have this whole sequence, we have tokens, and we say that for these tokens, this, and this guy, we say that they belong to the first bucket. Here we have the second bucket, here we have the third bucket, because all these guys are similar to each other according to our criterion, some criterion, and so we include them like 2, 1, 2, 3, 5 of them here, 3 of them with level 2, and 3 of them with level 3. This is what we get as an output of this bucketing procedure. And what we want to have in these buckets, we want, if they're similar, then the hashes will be similar. So kind of locality sensitive hashing. We want our hash function to like maintain these distances. We can say that if x1 and x2 are close to each other, then the hashes also should be close to each other. If they're distinct, then after application of hash functions, they will be far away from each other. And okay, we can definitely say that if we select the right number of buckets, then we have significantly better memory and time complexity, because we kind of compute attentions only within each bucket. To do this locality sensitive hashing, we draw two random hyperplanes, for example, and say that points in this embedding space that belong to this first guy goes to like the first bucket, this guy to the second, third, fourth. So now we have split by these two hyperplanes, and we have these indexes of cluster with this index 1, 2, 3, or 4 after hashing. So we kind of can split everything. There is another intuition that is quite similar in terms of, okay, this is exactly similar, but it's about that we project all points to a sphere. This is actually, okay, illustration from the article. And we see what is the angle for a particular point in a plane, maybe multidimensional angle. But again, this is in terms of mass is similar to what we was doing at previous slide. We just draw some random hyperplanes and say that we split our space to 4 subspaces, and we use hashing. Okay, for sure we can use not 2, but 3 or 4 subspaces if we need it. Also, as we do all this stuff in a random way, it can be the case that in some chunks, we have, like in some clusters, we have more points than in other clusters. And it kind of not very good, because our complexity equals to like k squared s, where s is like number of brackets, and k, okay, number of points in bracket, and it equals to k equals n. So large brackets affect the overall computational complexity and memory complexity. So we want to make them equal. And in this case, we say that if we have very large bucket, one bucket gives point to another one. And if you do the final split, we have similar size of buckets. And it's like this. So they're similar. But as we expect that this blue guy is close to the blue guys, maybe they need some attention between them. In this case, it's possible. We can say that we can have these backward attentions from here to here. And due to this, we still can manage links between different tokens, but also we kind of have an upper bound on the quality or all the computational resources that we need to devote to get results on the split chunks. Okay, and this is what is done to make it better. Also, second thing is about you need like a kind of different backpropagation to make it work, because we have this strange split procedure, but it's okay. We can somehow do it. I will not pay much attention to it. Okay, let's look at an example of results. The problem for this model, for this kind of reform, was to continue the images. So we start with this part, and we want to like again to generate like remaining part of an image. And as you can see, it's kind of pretty realistic back there. Not ideal, but okay, it's not GANs here. And you can see that with full attention, you have similar quality if we have many steps. And if we have like 16 hashes, then we kind of close to what we have with full attention. And more hashes give us higher score in terms of attention. So even if you try to apply to different areas, this reform attention is better. So what we can say as a conclusion of our lecture. We can see that for transformer, memory and computation requirements are high because the number of parameters are tremendous, and more of that, we need to compute attention between each token in input and each token in the output. In case of self-attention, it just makes the computational complexity and space complexity and squared. And in this case, we sometimes need something more rapid, faster to make transformers work. And especially it's important if you have like large sequences. In this case, we can try to use two ideas. The first idea is apply this sparse attention mechanism when we have not all-to-all connections, like not full connected layer. If you think about this fully connected classic neural networks, but instead we try to find what attention is good, what attention is bad, and what relations we should take. And another idea is to process them in parts. We can take this as a very base idea, so kind of we create embeddings of sequences, and for embeddings of sequences, we proceed further and provide better results in that. And we can go other way, and we can try to, not the other way, but we can try to improve on that with this bucket processing from reform transformers, when we somehow manage to split the tokens in some meaningful way, trying to make them work better. And I encourage you to read these papers carefully, because as you can see, there is very strange choice of hyperparameters in terms of the statements they make in abstracts in conclusions. Often, when we are thinking about this kind of behavior for transformers, we imagine these windows or number of global tokens, like very small, something what we have in convolutional neural networks. But actually, to make these models work and not to make them very deep, I suppose we need to make these hyperparameters very, very large, kind of similar to what we have before in BERT. From one point of view, we can say that it allows us to use pre-trained model. From other point of view, it also degrades the performance in terms of how fast they work and how fast they train. So you kind of should take into account this kind of thing when we are applying this large-scale transformer models. Okay, it's the end for the lecture today. Thank you for your attention, and I will be happy to see you the next Friday. And I suppose the last lecture is last Tuesday. On Friday, I suppose I will give this event prediction problem and how can we do it with and without neural networks. And on Tuesday, Yulia Gusak and colleagues will give some introduction on audio signal processing. What should you know when you want to process audio and what heuristics are useful, what are not in this case? I think it's very important in terms of the general topic of the course when we are trying to see how different sequential data processing are solved and what kind of ideas we can grab and put in your own context. So I was happy to see you all today. Have a good evening, and now it's Rodrigo time, so I will give him the right to do everything he wants right now.
Thank you, Alexei. We will start, we'll have a short break, so we'll start at 3, we'll start in 17 minutes. So now is so 5:03, and we'll start at 5:20.